Hello friends, we start a class on sequence of function. This is our class 10. In previous class we discussed a theorem on uniform convergence of a sequence of integrable functions and discussed the proof of the theorem and some examples on that theorem. In this class, we discuss a theorem on uniform convergence of a sequence of differentiable functions. Okay, theorem on uniform convergence of a sequence of differentiable functions. Okay. And some examples. Okay, a theorem, but we avoid the proof of this theorem. Okay, we state the theorem and some examples on this theorem. Okay, clear? Now let us start. The theorem is, let fn be a sequence of functions on AB. Okay, fn be a sequence of functions on closed interval AB, such that for all n belongs to n, fn dash x exists for all x belongs to AB. That is, for each fn, fn dash exists for all x. Okay, for each fn dash exists for all x. Now, if condition 1, the sequence of functions fn dash, okay, for each n fn dash exists, so this is also a sequence of function. Clear? So if this sequence of function is uniformly convergent on AB to a function g, okay, that is limit n tends to infinity fn dash x equal to gx for all x, and if the original sequence fn is pointwise convergent at least one point. The original sequence of function is pointwise convergent at least one point, x0 belongs to AB. Okay, if these two conditions holds, then we say that the sequence of function fn, okay, the sequence of function fn is uniformly convergent on AB, and if f be the limit function, okay, then f dash x equal to gx. Okay, this gx. Okay, f dash x equal to gx. Clear? That is f dash x means ddx of fx, and fx means limit n tends to infinity fn x, because fn is uniformly converges to f. Okay, and this is gx. Gx means limit n tends to infinity fn dash x, that is limit n tends to infinity ddx of fn x. So this implies the derivative and the limit can be interchanged. Okay, so we repeat again. If fn be a sequence of function and each fn is differentiable for all x, each fn is differentiable for all x, and if this sequence of function fn dash, this sequence of function is uniformly convergent to a function g, and the original sequence of function is pointwise convergent at least one point, x0 belongs to AB, then the sequence of function fn, that is the original sequence of function, is uniformly convergent on AB, and f dash x equal to gx. Clear? This is our theorem. Okay. Now first we give an example to show that only the first condition is not enough to ensure to prove the uniform convergence of fn. Okay, that is only the uniform convergence of fn dash only the uniform convergence of fn dash is not enough to ensure the uniform convergence of fn. Okay, that is the first condition is not enough to ensure the sequence of function is uniformly convergent. Okay, so we discuss this concept by an example. Okay, so our discussion is the condition 1, that is the uniform convergence of fn dash is not enough to ensure the uniform convergence of the sequence of function fn. Clear? This is our discussion. So we take a sequence of function fnx equal to log n plus x square. Okay, we consider a sequence of function fnx equal to log n plus x square. X belongs to 0 1. Okay, so for now we prove the sequence fn dash is uniformly convergent, but fn is not uniformly convergent. Okay, fn dash is uniformly convergent, but the sequence of function fn is not uniformly convergent. Clear? So fnx is this. So fn dash x equal to, if you derivative, 2x by n plus x square. X belongs to 0 1. Okay, now first we check it is pointwise convergent or not. So at x equal to 0, limit n tends to infinity fn dash 0 equal to 0. So this real sequence is convergent, and hence the sequence fn dash, the sequence of function fn dash is pointwise convergent at x equal to 0. Okay, we discussed in previous classes how to check if at a point a sequence of function is pointwise convergent. Okay, similarly at x equal to 1, limit n tends to infinity fn dash 1 equal to limit n tends to infinity for x equal to 1 2 by n plus 1. So 2 by n plus 1, this limit is 0. So the sequence of function fn dash is pointwise convergent at x equal to 1. Similarly, for 0 less than x less than 1, limit n tends to infinity fn x equal to limit n tends to infinity 2x by n plus x square. Since x is a non-zero real number, then this, and as n tends to infinity, this tends to infinity. So, and x is a non-zero real number, so this tends to 0. Okay, so for all x belongs to 0 1, close 0 1, the limit exists. So we say this real sequence fn x, this real sequence fn dash x, okay, is convergent for all x belongs to 0 1. Clear? This implies the sequence of function fn dash, the sequence of function fn dash is pointwise convergent on 0 1. Okay, and since for x equal to 0 the limit is 0, for x equal to 1 the limit is 0, for 0 less than x less than 1 the limit is also 0. So the limit function is, we take the limit function as gx equal to 0 for all x belongs to 0 1. Clear? So we have to prove, we prove the sequence of function fn dash is pointwise convergent on 0 1 and the limit function is 0. Now we have to prove that this is uniformly convergent. So we apply Mn test. So what is our Mn? We discussed the Mn test in previous classes. Okay, the Mn equal to supremum of x belongs to 0 1 fn dash x minus gx mod of. Okay, so this is equal to supremum of x belongs to 0 1. What is our fn dash x? Fn dash x is 2x by n plus x square. So this is 2x by n plus x square. Okay, minus 0. Clear? So this is supremum of x belongs to 0 1 2x by n plus x square. Okay, since x greater than equal to 0 and n is greater than 0. Okay, so So this is a non-negative term, so we remove the mod. Okay, we take this as a function hx. Okay, that is this equal to supremum of x belongs to 0 1 hx. Okay, we take this function as hx, that is this is equal to supremum of x belongs to 0 1 hx, where hx equal to hx equal to this, where hx equal to 2x by, where hx equal to 2x by n plus x square, x belongs to 0 1. Okay, clear? Now h dash x equal to n plus x square plus square, n plus x square into 2 minus 2x into 2x. Okay, so 2n plus 2x square minus 4x square by n plus x square the whole square. Okay, so 2n minus 2x square n plus x square whole square equal to 2 into n minus x square by n plus x square whole square. Okay, since x belongs to 0 1 and n belongs to natural number, so this is greater than 0 for all x belongs to 0 1 and for all n greater than equal to 2. Okay, if x equal to 1 and n equal to 1, if x equal to 1 and n equal to 1, then this may be 0. Okay, so this is greater than 0, this is greater than 0 for all x belongs to 0 1 and for all n greater than equal to 2. Clear? Okay, so hx is strictly monotonic increasing on 0 1. Okay, because we know if fx is greater than 0 on D, then f is strictly monotonic increasing on D. Okay, clear? So f dash x, if f dash x is greater than 0 on D, then f is strictly monotonic increasing on D. So here h dash x is greater than 0 on 0 1, then we say hx is strictly monotonic increasing on 0 1. Clear? So we have the maximum of hx at x equal to 1, because it is monotonic, strictly monotonic increasing. So at x equal to 1, h give the maximum value. So therefore supremum of hx, x belongs to 0 1 equal to h of 1, that is 2 by n plus 1. Clear? 2 by n plus 1. Therefore our mn equal to supremum of hx. So mn equal to supremum of hx, and supremum of hx equal to this 2 by n plus 1. This is tends to 0 as n tends to infinity. Okay, so by mn test this sequence of function, because our function is fn dash. Okay, so this sequence of function is uniformly convergent on 0 1. Okay, this is uniformly convergent on 0 1. Clear? But our fn x is log n plus x square. Okay, log n plus x square. And limit n tends to infinity, fn x does not exist for any x belongs to 0, 1. Okay, clear? Because if x equal to 0, then log n, limit n tends to infinity, log n which tends to infinity, and we can check for every x this is diverges to infinity. So there are no x belongs to 0, 1 such that this limit exists. So this implies this sequence of function is not pointwise convergent at not pointwise convergent on 0, 1, and hence not uniformly convergent on 0, 1. Clear? So we discuss, this is an example of a sequence of functions such that fn dash is uniformly convergent but fn is not uniformly convergent. So these statements will be proved. Okay, clear? Now we discuss another example. Now example 2. This example shows that the uniform convergence of fn dash is a sufficient but not a necessary condition. That is, the condition 1. In this theorem, this is our condition 1. That is, the sequence of function fn dash is uniformly convergent. In this theorem, this is a sufficient condition but not a necessary condition. That is there exists example such that fn is uniformly convergent but fn dash is not uniformly convergent. Okay, so now we discuss an example to prove this condition, that is the condition 1, is a sufficient but not a necessary condition. Okay, so we discuss that the condition, the uniformly convergence of the sequence fn dash, okay, is only a sufficient but not a necessary condition. Okay, clear? The uniform convergence of the sequence fn dash is only a sufficient but not a necessary condition for the uniform convergence of the sequence of function fn. Clear? To prove this, consider the example, that is which will prove, we prove fn is uniformly convergent but fn dash is not. Okay, we consider a sequence of function which is uniformly convergent but the derivative function, this sequence of function, is not uniformly convergent. Okay, so we consider the example fn x equal to, we consider the sequence of function fn x equal to x minus x to the power n by n, x belongs to 0, 1. Okay, this is the sequence of function. So first we prove this is uniformly convergent. So first we prove this is pointwise convergent. So at x equal to 0, limit n tends to infinity, fn 0 equal to 0. At x equal to 1, limit n tends to infinity, fn 1 equal to limit n tends to infinity 1 minus 1 by n. Okay, 1 minus 1 by n. Clear? That is, this is 1 because this is tends to 0, and at g for 0 less than x less than 1, limit n tends to infinity f n x equal to limit n tends to infinity x minus x to the power n by n. Okay, clear? So x is a non-zero real number, and 0 less than x than 1, that is x is a fraction. X is a fraction. So in graph, if we see, if we take x equal to half, then limit n tends to infinity x minus, that is half minus half to the power n by n. Okay, that is limit n tends to infinity half minus 1 by to the power n into n. Okay, so as n tends to infinity, this tends to 0 because half lies between 0 and 1. Okay, so for any real number lies between 0 and 1, this part converges to 0. So here x 0 less than x less than 1, then limit n tends to infinity, this part will converge to 0. So this is the limit is x minus 0, that is x. Okay, clear? So for x equal to 0, the limit exists. For x equal to 1, the limit exists. For 0 less than x less than 1, the limit is also exists. Therefore, the real sequence f n x, is convergent for all x belongs to closed 0, 1. Okay, this implies the sequence of function f n is pointwise convergent on 0, 1. Okay, and the limit function is, fx equal to 0 when x equal to 0, x when 0 less than x less than 1, and 1 when x equal to 1. Okay, say at x equal to 0, limit is 0. For x equal to 1, the limit is 1, and 0 less than x less than 1, the limit is x. So for x equal to 0, 0, for x equal to 1, 1, and for 0 less than x less than 1, x. So combining, we have fx equal to x for all x belongs to 0, 1. Okay, clear? At x equal to 0, 0, x equal to 1, 1, and remaining portion x. Okay, so this is our pointwise limit. Now to find the uniform convergence of f and x, we use the Mn test. So what is our Mn? Mn equal to supremum of mod of f n x minus fx, x belongs to 0, 1. Clear? So this is equal to supremum of x belongs to 0, 1 mod of what is our f n x? Our f n x is x minus x to the power n by n. So this is x minus x to the power n by n, and fx is x, this is minus x. Okay, so this implies supremum x belongs to 0, 1, x is cancel out, this is mod of x to the power n by n, the minus can be cancelled out. Okay, so equal to supremum of x belongs to 0, 1, x to the power n by n. Okay, clear? Because this is a non-negative term, x, since x is greater than or equal to 0 and n is greater than 0. Okay, so this is a non-negative term, so remove the mod. So this is equal to supremum of x belongs to 0, 1, x to the power n by n. Okay, clear? Okay, since this is a supremum on x, okay, run on x, so n is independent of x, so 1 by n supremum of x belongs to 0, 1, x to the power n. Okay, since n is greater than 0. Okay, because n is a real number, natural number, So n is greater than 0. So 1 by n supremum of x belongs to 0 1 x to the power n. So this supremum will be 1. So this is 1 by n into 1. So this is 1 by n. Okay. So our mn equal to supremum of this, and by calculation I get mn equal to 1 by n. Therefore mn equal to 1 by n. Okay. This tends to 0 as n tends to infinity. Okay. Therefore by mn test, this sequence of function is uniformly convergent on 0 1. Clear? So we prove the sequence of function fn is uniformly convergent. Now our fnx is x minus x to the power n by n. Therefore fn dash x equal to 1 minus x to the power n minus 1. Okay. Simply derivative x belongs to 0 1. Now we check this is uniformly convergent or not. So first we find the pointwise limit. Okay. So at x equal to 0, limit n tends to infinity, fn dash 0. For x equal to 0, this is 1. Okay. And for x equal to 1, limit n tends to infinity, fn dash 1. This is 0. Clear? Okay. Clear? And for 0 less than x less than 1, limit n tends to infinity, fn dash x equal to limit n tends to infinity 1 minus x to the power n minus 1. Okay. Since 0 less than x less than 1, limit n tends to infinity x to the power n minus 1 is 0. Okay. Since 0 less than x less than 1, this implies limit n tends to infinity x to the power n equal to 0. So also x to the power n minus 1 also 0. So this is equal to 1 minus limit n tends to infinity x to the power n minus 1. This is 1 minus 0, that is 1. Okay. So the real sequence fn dash x is convergent for all x belongs to 0 1. Okay, because at x equal to 0 this limit exists, at x equal to 1 this limit exists, for 0 less than x less than 1 this limit also exists. So this real sequence is convergent. This real sequence is convergent for all x belongs to 0 1. This implies this sequence of function is pointwise convergent on 0 1, and the limit function is fx equal to fx equal to 1 for x belongs to 0 1 and 0 for x equal to 1. Since for x equal to 0 1 and 0 less than x less than 1, the limit is also 1. So for x belongs to close 0 open 1, and for x equal to 1 the limit is 0. So for x equal to 1 the limit is 0. Okay, we call this function as g. Okay, we call this function as g because we already use f. Okay. Now so fn dash is pointwise convergent on 0 1, and the limit function is this. Since fn dash is continuous on 0 1, fn dash is continuous on 0 1. So since fn dash x is continuous on 0 1, this implies fn dash x is continuous at x equal to 1, but the limit function gx is not continuous at x equal to 1. Okay, the limit function is not continuous at x equal to 1. So this implies the convergence of fn dash is not uniform. Okay, clear? So we prove this is an example. So we prove this is an example such that fn is uniformly convergent, but fn dash is not uniformly convergent. Okay, fn dash is not uniformly convergent. Okay, clear? So this statement will prove with the help of this example. Okay, the uniform convergence of the sequence fn dash is only a sufficient but not a necessary condition. Clear? Now we discuss another example. Okay, now we discuss an example of mapa is number 576, like example 2. Okay, so what is our question? Question is, if f from R to R be uniformly continuous, okay, on R, if R to R be uniformly continuous on R, full stop, for each n belongs to n, fn x is defined by x plus 1 by n. Okay, x belongs to R. Clear? F is a uniformly continuous function on R, and fn x is defined as f of x plus 1 by n for all x belongs to R. Then prove that the sequence of function fn is uniformly convergent on R. Clear? Okay, this is our question. Now first recall a result. If xn be sequence in R, if xn be a real sequence and limit n tends to infinity xn equal to x. Okay, if xn be a real sequence which converges to x, and f is uniformly continuous on R. Okay, if xn is a real sequence and this sequence converges to x, if f is uniformly continuous on R, then the sequence fxn converges to fx. Okay, then the sequence fxn converges to fx, that is limit n tends to infinity f of xn equal to fx, that is f of limit n tends to infinity xn. Okay, that is if f is uniformly convergent, then the limit and f can be interchanged. Okay, so we use this result. Okay, since here f is uniformly continuous, since therefore limit n tends to infinity f of x plus 1 by n. This is equal to f of limit n tends to infinity x plus 1 by n for all x belongs to R. Clear? Because of this result, f is uniformly continuous on R, it is given. So limit of f x plus 1 by n equal to f of limit n tends to infinity x plus 1 by n. So now this limit equal to fx, okay, 1 by n tends to 0, so fx for all x belongs to R. Okay, clear? So this is our fnx, this is our fnx, this is our fnx. So we have, therefore limit n tends to infinity fnx equal to fx for all x belongs to R. Okay, yes. This implies the real sequence fnx is convergent for all x belongs to R. This implies the sequence of function fn is pointwise convergent on R, and the limit function is f. Okay, this is the given f, this f, okay, this f, okay, because limit n tends to infinity fnx equal to fx for all x, so the sequence of function is pointwise convergent on R and the limit function is f. Clear? Now we have to prove that fn is uniformly convergent. Okay, clear? Since f is uniformly continuous, so now we apply the definition of uniformly continuous. Since f is uniformly continuous on R, then for each epsilon greater than 0 there exists a delta greater than 0 such that mod of fx minus fy is less than epsilon for all x comma y satisfying mod of x minus y less than delta. Clear? So uniform continuous, this is the definition of uniform continuity. Okay, for each epsilon greater than 0 there exists delta greater than 0 such that mod of fx minus fy less than epsilon for all x y satisfying mod of x minus y less than delta. Clear? So this implies mod of x minus y less than delta therefore this implies mod of fx minus fy is less than epsilon. Okay, if the difference of two real number is less than delta, then corresponding to that real numbers fx minus fy is less than epsilon. Clear? Okay, now since we have a delta, there exists delta, so for this delta, now we take this delta, so now we take this delta which is greater than 0 and 1 is greater than 0, then by Archimedean property, there exists a natural number n, there exists a natural number k belongs to n. Okay, there is a natural number k belongs to n such that k delta is greater than 1. Clear? K delta is greater than 1. This implies 1 by k is less than delta. 1 by k is less than delta. Now if n greater than or equal to k, this implies 1 by n is less than or equal to 1 by k, which is less than delta. Therefore 1 by n is also less than delta for all n greater than or equal to k. Clear? Okay. So x plus 1 by n minus x plus 1 by this mod, x plus 1 by n and x, these two real numbers. The difference of two real numbers is equal to 1 by n, which is less than delta for all n greater than or equal to k. So now see this. If mod of x minus y is less than delta, this implies fx minus fy is less than epsilon. Okay. So here mod of this minus this is less than delta. Then mod of f of x plus 1 by n minus fx is less than epsilon for all n greater than or equal to k, because this is less than delta for all n greater than or equal to k. Here we use this equality. Okay. If mod of x minus y is less than delta, implies mod of fx minus fy is less than epsilon. So here we find mod of this real number and minus this real number is 1 by n, which is less than delta. So mod of this minus this is less than delta, which satisfies for all n greater than or equal to k. Then f of this, mod of f of this minus f of this is less than epsilon for all n greater than or equal to k. Clear? So this implies this is our fnx. Fnx minus fx is less than epsilon for all n greater than or equal to k. Clear? Fnx minus fx is less than epsilon for all n greater than or equal to k. So this implies the sequence of function fn is uniformly convergent. We will discuss the definition in previous classes. This is our definition of uniform convergence. So the sequence of function is uniformly convergent to f. Okay. So we prove the sequence of function is uniformly convergent on R. Okay. Clear? That's it. Thank you.